Welcome. Thank you for joining. This is going to be the midterm review for Math 146. We're going to talk a little bit about the test first. See if I can get this pen working properly. We're going to go with just 20 questions. The questions will come from chapters 1 through 5. All right. And it'll be pretty much spread out pretty evenly. So maybe 2 to 3 questions from different chapters. I will say that section 5.3 is not on test. So that should limit your preparation. We're just not responsible for that particular unit. All right. And there's none on the practice either. And let me add that there is a new practice midterm. And basically, it's not really new, it's more updated. So it has the original problems as the old one did, but I've added a total of 35 questions. I figured it's a good idea to look at a few more questions. I will say that the practice midterm doesn't count. So even if you do get a score on it, that score will be eliminated. It will not count at all. And be sure that you can actually, if you want to type in the chat during this live stream, I am monitoring the chat as well. The plan tonight is just to look at some problems, do some problems, talk about some things. I will say this, that the practice midterm is, or I should say contains, the question, the pool of questions. And what I mean by that is that it is probably the best study guide, because a lot of those questions will be like the original questions on the midterm. And so the practice has 35 questions. the midterm has 20. Obviously, there will be problems not on the midterm or on the midterm that's not on the practice and vice versa. Let me share how you would actually go and access the updated midterm. So it is below the midterm one, and I just kept it there because other students have already started it. So if it is deleted, don't worry, I can bring it back. But the same problems in the practice one are also in the practice updated one. It's just that the updated one contains more. So you might as well move toward the new updated version because it has everything in one place. All right. So you do have multiple attempts at this thing. And if you exhaust all of those and it closes out on you, just let me know. I may change the due date to the 26th. It shouldn't be the 27th. All right. And the reason is because on the 27th, that is when the test opens up. The midterm test opens up on the 27th, and it stays open for those 3 days. So what we'll do is look at a couple problems and try to get a feel for some of these problems. Um, and then we will also do some problems that um, you might want to do. Now, let's just, and really, it's just really about understanding the question, reading the question, um, trying to figure out what they want, what they're trying to understand, and then selecting the best choice. So for the first one, it says determine whether the results, and this is a chapter 1 type of problem. Determine whether the results below appear to have statistical significance, and also determine whether the results have practical significance. Now, I probably will say that more than likely something like this probably will not be on the actual midterm, just because it can be misinterpreted. And I've seen students ask questions about this particular type of problem, and it wasn't really obvious. And even after the answer was identified, um, one could still argue another way just on how the question was actually posed. So first things first is it says, in a study of a weight loss program, 7 subjects lost an average of 41 pounds. Now, that sounds extremely significant. I mean, they were in the weight loss program, and as a result, the average weight loss was 41 pounds. Now, they also say it is found that there is about a 40% chance of getting such results with a diet that has no effect. Well, in other words, these results could have happened with a 40% chance. So we're basically just taking out all the information. And let's just kind of analyze this problem a little further. And what we'll do is think about 7 subjects and the loss 41 pounds. Now, the truth is that this could be misleading. The reason why is because we don't know if all 7 subjects lost 41 pounds and they averaged that together. Or could it be that one subject lost maybe 100 pounds and everybody else didn't, and the total average turned out to be 41 because of that one outlier? We don't know what all the data is. We don't have a chart of the data to analyze it to see if the average is a good measure of center. But what we can say for certain is that this does have a significance because there was loss happening, and that's exactly what we needed to happen. So what we'll do is say the program is statistically significant because the results are unlikely to occur by chance. All right, now if there were an 80 to 90% chance of getting these results, then probably the weight loss program had no real effect. Now, does the weight loss program have practical significance? I would say yes as well, because it actually has a practically significant amount, um, because the amount of weight loss is considered practically significant as well. Let's look at another question here. It says a researcher was once criticized for falsifying data. Among his data were figures obtained from 7 groups of subjects with 20 individual subjects in each group. These values were given for the percentage of successes in each group. What's wrong with these values? Well, that's a good point. Because there are 20 individuals and you're trying to calculate the percentage of success of each group, 20 is that type of number to where every percentage is going to be either 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100%. The percentages should be multiples of 5. That's the thing about 20. 1 out of 20, 5%. 2 out of 20, 10%. 10 out of 20, 50%. Okay? 18 out of 20, 90. So on and so forth. So yeah, I mean, we can just, there's really nothing really to calculate. A lot of the problems from the first part, from the first chapter, were very conceptual type of problems. There wasn't much to calculate. You really just had to understand it and go through each one. Determine which of the 4 levels of measurement is most appropriate for the data below. And it says years in which a war was started. And then we have nominal. It says the nominal level of measurement is most appropriate because the data cannot be ordered. The interval level of measurement. is most appropriate because the data can be ordered, the differences can be found and are meaningful, and there is no natural starting 0 point. Here we have the ratio level of measurement is most appropriate because the data can be ordered and there is a natural starting point. The ordinal level of measurement is most appropriate because the data can be ordered. Now, keep in mind, because we're talking about years, and years is a numerical type of measurement, it is between ratio and interval. Now, nominal and ordinal deals with categorical type of data. So you do got to know the difference between those four different types of measurements. What I will say though is that the truth is, in practice, we don't really use the four levels of measurement. The history of the four levels of measurement stems from psychology. Okay, they use those type to classify different measurements and things of this sort. Well, here's the thing. Time is a never-ending type of concept. The truth is. Now, if you think of time as numerical, yeah, there was a 0 in terms of the years. 2020 years ago, there was a 0. But that's not a natural 0. Um, time is basically um, infinite, I would say. So for that reason, we're going to say that it's an interval of time. The level of measurement we'll choose is an interval because we're dealing with time that the war started versus ratio, where we're talking more about the height, the distance, the lengths, the volumes, things like that are measured from 0 to some other number. Here's a question. Let me make my screen a little bigger just so that we can all see clearly. So we're just working some of these out, just trying to get a feel for some of the questions. The histogram to the right represents the weights of members of a certain high school math team. So it looks like from 110 to 119, 2 people, so on and so forth. The histogram represents blank math team members. So in other words, you'd have to think about the sum of all the frequencies. And all the bars match up to a certain frequency. If we can add up all those frequencies, we'll know the population of that team, the number of people in that team. So it's just a matter of adding them all up. We could do 2 plus 4 plus 1 is already 7, plus 3 is 10, another 10 is 20, and then 23. So you can just go with 23 total because we're adding them all up. Okay. What is the class width? Well, the class width should be the same for every interval in there. And it is the difference between the high and the low, so it'd be 20. Remember, these little bins are also called classes. Now they ask another question. What are the approximate lower and upper class limits of the first class? Well, the first class is from 100 to 120. So I'll go with 100 to 120. Here's another one. if A denotes some event, what does A bar denote? And this symbol stands for the complement of A. It is the opposite. So if A is it will rain, A complement or A bar is it will not rain. So if the probability of A happening is 0.998, that's a very high percentage. That's 99.8% chance of happening. What is the value of the probability of it not happening, of A not happening? And what does A denote first? So what it denotes is that it is the complement of A, that they are mutually exclusive. They are disjointed. They have nothing in common. So C is not fully correct. It's true that it denotes the complement, but the meaning that A complement and A share some outcomes is it cannot happen. So D is the more accurate response. Event A bar denotes the complement of A, meaning that A bar consists of all outcomes in which event A does not occur. All right. What about the probability of A complement? Well, you'd have to know that the formula for calculating the complement, and if I scroll down, it's actually going to be 1 minus P bar, or probability of A. So the probability of A bar is equal to 1 minus the probability of A, but we know what this is. It's 1 minus that. So we can just say it's going to be 0.002. Assume that 1,400 births are randomly selected and 1,376 of the births are girls. That, by the way, that is extremely rare. That is unlikely to happen by chance. There's usually a 50-50% chance of a girl or boy. So in 1,400 births randomly selected and 1,376 of those births are girls, use subjective judgment to describe the number of girls as significantly high, significantly low, or neither significantly low nor significantly high. So I think it would be best to say that it is significantly high for that reason. This particular problem is not going to be on the test. We're actually omitting the probability of odds. It's just a simple formula that you would use, but we're not calculating those odds. We're not using that. So for this one, you can simply skip. Find the indicated complement. So it says a certain group of women has a 0.31% rate of red-green color blindness. What would be the complement? Well, they give you it as a percentage, so it would be 0.69%, which is really just 0.00. Wait a minute, hold on. It'd be more like 99.69%. And if we convert that to a decimal, 0.9969. Okay. Yeah. That was a little tricky. A certain group of women has 0.31% rate of red-green color blindness. If a woman is selected at random, what is the probability that she does not have red-green color blindness? And they don't want you to use it as a percentage. So 0.31% though, I will say that's kind of a tricky question, I think, because if you're talking about that is really equal to that. Um, and then the complement again would be 99.69% because the complement and the event must make 100% or one whole. And that's what gives us this. So if you were to add those two together, you would get one whole there. So what will we put in for our answer? 0.9969. Assume boys and girls are equally likely. Find the probability of a couple having a baby girl when their sixth child is born, given that the first 5 children were all girls. There's a lot of combinations in this type of event. All right, this is actually a pretty interesting question. Let's copy this question over and analyze this question a little bit more. So again, we're assuming boys and girls are equally likely, which basically means the probability of a boy is 1/2, probability of a girl 1/2. Find the probability of a couple having a baby when their child is born. Do they mean a baby girl? Find the probability of a couple having a baby. Well, yeah, I mean, the probability of a couple having a baby is going to be 100%. What else could they have? Um, given that the first, oh, okay, maybe it didn't copy properly. So I'm going to check and see. Okay, a baby girl when their sixth child is born, given that the first 5 children were all girls. All right. There's a few ways we can go about doing this. All right. One way we could do what we could do is think about. Um, let me go back to the problem. There's 6 kids, 5 girls, Find the probability of a couple having a baby girl when their sixth child is born, given that the first 5 children were all girls. Well, okay. We can do this at least 3 different ways. Basically, what's the probability of having 6 girls in 6 births? Now, that's a lot of different combinations. I mean, if you do 2 to the 6th power, that's 64. Six girls, there's only one of them out of the 64. That's only one possibility. You're either going to have, we're not going to count all 64 cases, but you can have 6 boys. This is the only unique case. You can have 6 girls. And then you can list the other 30 combinations. There's not 30, 60, there's 64 altogether. So I just listed 2 out of the 64. I mean, I can change the first one to a girl and the rest boys. I can change the second one to 2 girls and the rest boys. I mean, there's going to be 64 different possibilities. And the way we were able to do that was knowing that basically there's 6 different spots. And first birth, second, third, fourth, fifth, sixth. There's 6 of them all together. So the first outcome, there's 2 different possibilities. And another 2 different possibilities, 2 different possibilities, 2 different possibilities, 2 different possibilities, and 2 different possibilities. And if you multiply them all up, that's 2 to the 6th power. But if you multiply that, again, 2 times 2 times 2 is 8. 2 times 2 is 8. You multiply all of that up, you're getting 64. But the problem is that there's only one out of all 64 combos. There's only one girl, 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 girl combination. So that's why the probability of that happening is going to be 1 over 64. I mean, that's one way to actually do it. I mean, the other way would be to actually just multiply the probabilities of each one. I mean, you had a 1/2 chance of a girl in the first birth, 1/2 in the second, 1/2 in the third, 1/2 in the fourth. Oh, make this clear for everyone so you can see this clearly. Another way to approach this problem, which is probably the more practical way, that more people probably did it this way. You could think of it as in the first birth, 1/2 times another 1/2 times another 1/2 times another 1/2. And there it is. I mean, we have the probability of having a girl in each case. And you multiply all those probabilities up, you're going to get 1 over 64. All right, I think we've done that one enough. Let's look at a couple more. So in this case, we have a chart. Now, sometimes for the chart, you can export it in Excel and do other things, but this is a tiny little 2x2 table. You don't have to export it. We can just work with it as is. So the data represents the results of a test for a certain disease. Assume one individual from the group is randomly selected. Find the probability of getting someone who tests positive given that he or she did not have the disease. All right. Because it says that it's given that he or she does not have the disease, we know that it's out of the total number of people who didn't have the disease. So we simply have to find the probability of getting someone who tests positive, and they didn't even have the disease. So it's restricted. It's not going to be 122 out of the whole thing. It's going to be 122 out of all of those. Actually, not even 122. Find the probability of getting someone who tests positive given that he or she did not have the disease. So it's actually going to be 15 people tested positive and they did not have it out of the total number of people who took it. Because it says this given part, we're restricting the total number of people to all the people who never had the disease. So 15 over 139 plus 15. And you can add that up. I mean, that's 15 out of 154. And they actually want you to round it to 3 places. So here we go. We can do that. 15 divided by 154. And keep in mind, the 154 is coming from the 15 and 139. Let's double check that. And now they want us to round it to 3 places. That's going to be 0.097. Any questions up to this point right now, or should I just keep going, or is anyone still watching the live playback? So feel free. Good evening. Yes. Glad you can make it. You're here live, and we're just getting into it. You know how it gets. Starts to get hard. We just did all the easy ones, and at the very end, we're going to check and see how well we did. Hopefully, I get an A. Well, you know how it gets though. It does get harder. Oh, you haven't missed much. We've just been reviewing the updated practice midterm, and it has 35 questions on it. Well, there's a lot of questions on this thing. So here's another question here. The author always uses girls on all either pregnant girls or girls. I don't know why he always says this. The table to the right lists probabilities for the corresponding number of girls in 3 births. All right. So the number of girls in 3 births. So in 3 births, you can have 0 girls, you can have 1 girl, you can have 2 girls, or you could even have all 3 girls in 3 births. And we have the probability of all of that. And we need to make sure it is a probability distribution. The sum of all these probabilities have to total 1. If it doesn't total 1 whole, then it's not even a real probability distribution. It does total 1. I just added it up. So we're good there. Now let's see, what is the choice? What is the random variable? What are its possible values? And are its values numerical? Well, the random variable will be the girls. So it's the x, the number of girls. The possible values are 0, 1, 2, or 3. It's just totally random. We don't know which one it's going to be. And then the question is, are the values numerical? Yeah, the values are numerical. So I'm going to go with, we have to read all 3 of them. B looks pretty good. You guys with me on that one? B seems good. Um, we actually don't do the expected value and net profit. So I'm gonna omit this one because we just don't do it, and it's not going to be on the actual test. So for that reason, I'm just going to put in some random numbers. I mean, we could do it. I remember how to do it, I think, but the problem is we're just not going to do it. Just because I don't want to focus on something that's definitely not going to be there. It somehow just squeaked in. I don't even know why it's even there. Determine whether or not the procedure described below results in a binomial distribution. If it is not binomial, identify at least one requirement that is not satisfied. You know, this is the kind of question where you really just have to remember what the definition of a binomial theorem is. Why were they numerical? Well, numerical is dealing with numbers and fractions as well. Remember there's 2 types of numerical numbers. Let me go back real quick. There was a question that I just saw about how did we know for sure that it was numerical? So numerical falls under 2 different categories. There's the discrete, and then there's continuous. Oh, I think I just misspelled that. I'm going to try that one more time. All right, we'll just leave it like that. Now, that data that they had, those were numbers like these numbers, these types of numbers are continuous. Discrete numbers are whole numbers. But either way you go, they're all under the umbrella of numerical. So we were fine there when we said that. When we when we, in the last problem, they don't let us go back. We should be able to go back if we wanted to. So it says 700 different voters in a region with two major political parties, A and B, are randomly selected from a population of 4,000 registered voters, each asked if he or she is a member of a political party A. Record a yes or no. Yeah, this is fine. We have a random sample from 4,700, and it's a yes or no type of recording. The only other thing that oh yeah, no, we have it. Looks like it's satisfied. Um, and again, I could pull up the definition of binomial probability distributions if you need to, but it outlines it here. The number of trials are fixed. The trials are independent of each other, and the sample is more than 5% of the population. Um, but wait a minute, there does appear to be one requirement that's not quite identified, and that's the probability of success. Yeah, so yeah, sure. I can go over the definition of that. Let me pull up that question real quick. Hold on. I'm going to zoom in on this so we can see it very clear. Um, so this is the chapter. Let me get there. Hold on. Page 199. All right. So let me zoom in on this. This comes from section 5.2. And so they define it and then they give some examples of what a binomial probability distribution really looks like. So there's 4 criteria. It's the procedure has a fixed number of trials. The trials are independent. So the people were the trials. And being that each person is different from the other because they're randomly selected, they're not a group all voting together. they don't know what the other one selected. That meant that they were independent. And then each trial must have all outcomes classified into either two categories. You're either yes or no, or success or failure, on or off. And the probability of success remains the same in all the trials, which means in our case it was a 50% chance you're either yes, or a 50% chance you're either no. So it's true. We did have a binomial probability distribution. Here's some more kind of the mechanics of how you would use this. And here's a question here. It says, when an adult is randomly selected, there is an 85% probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of the 5 randomly selected know what Twitter is. First of all, does the procedure result in a binomial distribution? And so we could say, yes, the number of trials were 5 because we randomly selected 5 adults. So there's 5 trials. All 5 people are independent because the adults were randomly selected. Here's another one. Each of the 5 trials has 2 categories of outcomes. And the outcomes are they either know it or they don't. So it's either yes, they know, no, they don't. And then the probability has to stay the same for every person. And it's 85% probability that the person knows what Twitter is. And if all 4 of those are satisfied, then yes, it is a binomial probability distribution. And that's kind of what we have here. 700 different voters in a region with 2 major political parties. The parties are A and B, are randomly selected from a population of 4,000. So 700 is the number of trials. It's more than 5%. We also have they're independent. And they're asked if they're either a member of party A or B, and that's it. It's either yes or no. And they belong to either one or the other. So the probability is always going to be that 50% chance that it's not going to change at all because they belong to one or the other. So this is definitely a binomial probability distribution. Was that helpful? I know that this has kind of been a long time since we've seen some of this. But that should be a review. That's all you need to know about that. So here's another question now. Now we're getting into, oh yeah, no problem at all. No problem at all. So here, now we're getting into the mean, the median, the mode, and the mid-range. We have a data set, and it's the jersey numbers of 11 players randomly selected from a roster of championship sports teams. What do the results tell us? Well, the results won't tell us anything really because they're jersey numbers. They don't have real numerical value. They're actually categorical value. But we can still find the mean. We can find the median, the mode, and the mid-range. So what we'll do first is I'm going to show you how you can find the mean and the median using the calculator. We're going to put everything into a list. So you just go into Stat and then Edit. Okay, my lists aren't clear, so I'm going to clear out my list real quick. Let me clear out list 2 as well. Alright, so I'm just going to put a bunch of the numbers into a list. This is usually the basic step that you would do. So now that I have all 11 numbers into my list, I just need to make sure I didn't make a mistake. So I'm going to print my list on the home screen. That looks pretty good. I should be able to go over to see all the numbers, but right now, for whatever reason, it's not. Now, where do you go to actually get the mean? Well, there's a couple places, guys. There's a few places we can do this. And I guess I can show you both ways. To get the mean, you can go into Stat, Calc, and then 1var Stats. 1var Stats, I'm going to do L1, and that's going to give me the mean. It's going to give me a lot more than the mean. It's also going to give me the median and other things as well, even the standard deviation. So 1var Stats is actually pretty powerful. I'm going to start over. Let me show you one more time. You go into Stat and then over to Calc. And then 1var Stats, put in L1, and then enter. X bar is the mean, 41.18. They want me to round it to just one decimal place, so I'm going to put 41.2. What about the median? Well, if you scroll down, they actually gave me the median. It's the MED. Now the mode, you're on your own. You have to figure that one out yourself. But it's not going to be too hard because the mode is the number that appears the most. So it's just a matter of scanning the problems and looking to see if you see any number that appears more than the others. Well, right now it looks like every number is appearing the same number of times. I don't see one number that has repeated itself. So I'm actually going to say there's no mode. Now the mid-range is the difference between the highest and the lowest divided by 2. So it's the range, but then half of the range. So the high is 89, the low is 1. If I subtract them, I get 88. And if I divide that by 2, I get 44. And what do we say about the results? Well, the results will be meaningless. What do the results tell us? Jersey numbers are nominal data. That is correct. They're not numerical. They're categorical. They're nominal. And they do not measure or count anything. So the resultant statistics are meaningless. Yeah, I'll go with that. Which of the following is always true? In a symmetrical bell-shaped distribution, the mean, median, and mode are the same. Yes. This looks like the same kind of problem. The only difference is they're asking for the range, the standard deviation, and the sample variance this time. What do the results tell us? Nothing, because the Jersey numbers are nominal. But this does bring up a good point. Where do we go to get the range, the sample standard deviation, and the sample variance? Remember, there are two different types of standard deviations. And you have to know the difference between them. We're really starting to warm up now. um, there's the sample standard deviation, and then there's the population standard. They're calculated differently. So we have to know, which one are we talking about? Are we talking about a sample? Are we talking about the real population? And they told us it's the sample. So the sample is little s. If it was the population, it'd be little sigma, which is the Greek letter for s. But we're talking about the sample standard deviation. Now in the calculator, they call it S sub x because x is the data. We're taking the sample standard deviation of the data. Yes, absolutely. Um, the sample is the statistic, and the parameter is going to be the population. I posted that you can get this calculator if it's not too late. I posted a link in our class in the discussion. I don't know if this one, I don't think this might work. Yeah. I can find another one for you. Here it is. Oh, they may have, they still might be doing it. There's a 90-day free trial for students because of COVID. I don't know if they stopped it or not. It's still there, and I can put it in the chat. So, I think I exited out of the test. I don't know if I'll be able to get back in there. All right. It looks like did they just boot me out? All right. I'll just, what I'll do, I'm going to submit the test. what happens is when you submit the test, you get to review the test with the correct answers. And we actually should be able to um, print it out as well. So all 35 questions, and what we can do is speed up our review. So what I'll do is I'm going to print it to OneNote, and we're going to pick up our review. And what I'll do is create a new. I'm gonna send it in there. All right, let's just. I have the entire test with the problems, and yeah. Now the first one, they have, what do they have? It's practically significant, but it's not statistically significant because the results are likely to occur by chance. And they have a different number than what we had last time. They have 27% chance of getting the results. Actually, 27% chance, that's kind of rare. That means, like, I guess the takeaway from this is you need 5% chance in order to be statistically significant. Whenever there's a 5% is always the threshold in statistics. It is a critical number. Yeah, no, the calculator program is pretty nice. I mean, let me show you that I actually have 3 calculators that I can choose from, and they're all fully functional. Okay, I can turn on Stat Wizard, Stat Diagnostic, all of that. Turn on those things. Make your calculator more powerful. And after the 90 days is up, you could buy it for pretty cheap. They'll just sell it to you. Oh yeah, you were doing it by hand? Oh no way, man. Okay, that's hardcore. Good job if you were doing that by hand. Um, we can now look at all of the questions a little faster now. That was a trick question. Let me zoom in on this. I don't like trick questions, not for the test. I don't. But that is something that you got to watch out for. There are a lot of trick questions out there. Assume boys and girls are equally likely. Find the probability of a couple having a baby girl when their 5th child is born, given that the first 4 children were all girls. Well, because it's all independent, they're asking for the probability of a couple having a baby girl. It's just 1/2 still. But if they ask the question, what is the probability of having 5 girls? That's 1/32. There's 32 different possibilities. 2 to the 5th power is 32. So the chances of them having 5 girls and 5 births is 1 out of 32 chance. That is low. I think that's less than 5%. Let me double check that. Well, 1 over 20 is 5%, so 1 over 32 is going to be, yeah, that is statistically significant to have 5 girls and 5 births. But the chance of still having a girl every time it's a 1/2 chance. So you really have to identify the kind of problem you're doing. Some of these problems may look like a chapter 5 or chapter 6 problem, and it is just a chapter 1 kind of problem because they vary in level of difficulty. So question identification is key in this course. What is the symbol for standard deviation? A sample standard deviation, little s. What is the symbol for population standard deviation? Well, that's little sigma. So there. All right. Variance is the standard deviation squared, the sample variance, and the population variance is little sigma squared. Sometimes they'll just say V. And keep in mind the square root of V is S. Consider a value to be significant low if the z-score is less than or equal to -2, or consider to be significantly high if its z-score is greater than or equal to 2. And so we have a data set lists weight of a type of coin. Those weights have a mean of 5.31 grams and a standard deviation of 0.05. Identify the weights that are significantly low or significantly high. Well, if I subtract 2 deviations from it, it will be significantly low. And that's exactly what they did. So let me show you. All they did was take the mean which is 5.31551, and they just subtracted the standard deviation from it twice. I'll do it once, and then I'm going to subtract it again from 0.05234. And what do I have? I have 0.521083. 0.521083. What about weights? Yeah. What about the numbers extremely high? Well, they're going to add 2 deviations to it. All right, here's a box plot. I actually might not put this one on there because we didn't really talk too much about box plots. I don't know. I mean, maybe we did. Actually, yeah, no, wait, I think we did. Keep in mind that in order to make a box plot, you have to have the 5-number summary. You have to have the low, the minimum, the low quartile, the median, and the upper quartile. So we have it, the min, Q1, This is also called the lower quartile or the 25th percentile. The median, we can call it MED. Q3 is the upper quartile, and then the maximum number. These all correspond to the 5-number summary, and our calculator does the 5-number summary. Remember, if you have a list like we do, I can go into one var stats, do L1, and I will get the 5-number summary. All right, I don't have a, let me go back to my other calculator. There's my 5-number summary. The min is 1, Q1 is 18, median 46, upper quartile, and the maximum. They want you to do it again. Find the 5-number summary given this data set, and then you write it in there, and then you choose which box plot corresponds to the 5-number summary. They're nearly identical. I can't even see B and C. Determine whether the description corresponds to an observational study or an experiment. And in order for something to be an experiment, you have to have a result. If there's no result, there's no experiment. Observation study is usually just for writing and to determine if you should do an experiment or not. But observational studies are pretty powerful, though. I think it's easier to conduct an observational study than it is an experiment, and it probably would be less biased in an observational study as well, especially if you're observing without anyone really knowing. You're going to get their true behavior. In an experiment, it's always simulated. There is a degree of surrealness to it. Even with placebos and stuff like that, it's just people will change. Maybe there's an incentive for people to go through it, and so they're more likely to act a certain way if they're desperate. So just, I don't know. 24. Determine whether a study is an experiment or an observational study. This is from chapter 1 type of stuff. I don't know how much you'll actually see of this. 25. Identify the type of sampling is used. Is it random, systematic, or systemic? Convenient sampling, stratified, or clustered? Identify the type of design the experiment has. Matched pairs, randomized blocks, so on and so forth. Well, the drug is designed to treat insomnia. In a clinical trial of drug, the amounts of sleep each night was measured before and after the subject had been treated with the drug. So you're going to take that data and match it up with the other data. And so for that reason, it is a matched pair type of design. Determine whether the result is a statistic or a parameter. All right, remember, a statistic comes from a sample, a parameter comes from a population. 28, determine whether the value below is a discrete or continuous data set. And both discrete and continuous are numerical, but there is a big difference between discrete. Discrete is a whole number, continuous is not. 701 couples used the XOR method, and 414 of them had baby girls. That's discrete. Okay. It's true that the probability of an event or its complement is exactly 1. Something is going to happen, for sure. And so we know that is definitely true. This is straight from the textbook. And this is just a probability of complement. 82% believe that you shouldn't lie on your income tax. What are the probability that someone does not believe this? And we say it's 18% or 0.18. There was just a few more. Remember, there are 35 questions on the updated midterm exam review. 35. Let's look at number 31. You have a table. I think this one even popped up on the quiz. I don't want to get too deep into this one, but it's just an or, but there's overlap. So you want to subtract one out. All right. Find the probability of getting an order for restaurant A or an order that is accurate. Well, I could say restaurant A is here, or an order that is accurate is here. $317 is counted twice. You don't want to count that twice when you add up all the numbers. That you divide by the total number. They don't give us the totals, so you actually have to create the totals yourself. Same type of problem. If an order is selected, find the probability of getting an order from restaurant A or D, or an order that is not accurate. So we have A or D. Those have nothing in common. Or an order that is not accurate. Well, that's from here. 36 and 16 is in this set. You don't want to count it twice. So when you're doing the probability, you're going to do 311 plus 143 plus 36 plus 51 plus 39 plus 16 out of the total number of people in the chart. So all of this plus. It would be a mistake to do add up the 30, add up the A, add up the D, and then add up this one, because you would have counted the 16 and the 36 twice, and there's no need. They were already accounted for. Another one. If 3 different orders are selected, find the probability they are all from restaurant C. So, okay, let's see. See the best way to do this. If 3 different orders are selected, so the total number of orders from restaurant C, let's figure out the probability of the first one being from C. it would be 274 out of the total. Well, let's figure out the total. 355, 334, 274, and then 144. So what I'll do is add them all up in my calculator. $355, let's make sure that's right. 334, actually that's 234. So 355 and then 234. No, wait, hold on. Yeah, that's 334 plus 274 plus 144. And now we're going to do 274 divided by 1107. That's the probability that the first one was from restaurant C. We're going to multiply it by itself again. And we're going to multiply it by itself one more time. No, I did it wrong. Here, let me clear that out. It was right up until a point, and then when we did, let's try that one more time. Oh wait, hold on. I'm pretty sure I should be able to recall that. All right, hold on. I'm gonna use a different calculator. Yeah. All right. So let's do this one more time. 355 plus 334 plus 274 plus 144. 1107, and we're going to do 144 divided by 1107. And all we have to do now is take this to the third power, multiply this by itself 3 times. Actually, not 144, 274 over there. And now we got 0.2475. We're going to take that number to the third power because there's 3 attempts. We got 0.0151, and that's exactly what they got for their answer, 0.0151. All right. I like number 34. We're going to do number 34, and let's take a peek at what else is left. (34) and 35 are similar. They're the binomial probability distribution function. They're both binomial probability distributions. All right? You either have a smartphone or you don't. They're independent and it's random. The probability of success is 56%. The number of trials is 16. Actually, 20. There are 6 people that got exactly right. So it says, assume that when adults with smartphones are randomly selected, 56% of them use them in meetings or classes. Okay, so 56% of adults use them in meetings or classes. If 20 adult smartphone users are randomly selected, find the probability that exactly 16 of them use smartphones in the meeting. 16 out of the 20. What is that probability? Well, what we're going to do is use the binomial probability function. So on our calculator, I'm going to show you where it is, clear out everything. It's going to be under distribute. So second, distribute, and you're going to go all the way down to Binomial Pdf. This is the one we use when it's exact amount. And if you're not sure what parameters to put in, because it accepts three things: the trials, the probability, and the x. So, let me do that one more time. The trials is 20. The probability is 0.56. And the exact amount is 16. Now, if you didn't know the order, you could use StatWizard, but I got 0.0169. Round it to 4 places, so you're actually going to get 0.0170. Now, what you can do is turn on StatWizard. Go to Mode, and then go to StatWizard, turn that on. And now, when you use Binomial Pdf formula, it will prompt you on what to enter. So here's the next problem. It says, assume that when adults with smartphones are randomly selected, 47% of them use them in meetings of class. So this time we're dealing with the probability is 47%. 13 adults, so our number of trials is 13. But this says, find the probability that fewer than 3 of them use their smartphones. So that's x is going to be actually less than 3, meaning either probability of 0, probability of 1, plus the probability of exactly 2. These are the 3 possibilities, and you would add them all up. So we could do what we did in the previous problem, just do 3 of them and add them all up, or we could get fancy and use not Binomial Pdf, but Binomial CDF, the cumulative density function, because that will accept the number of trials, the probability, but the x value will accept the numbers that are less than amount. So we put in everything fewer. So we would go from 2. I'd put in 2, which stands for 2, 1, and 0. At most 2 or fewer than 3, they mean the same thing mathematically. So when I come back to my calculator, this time I'm going to do Binomial CDF. My trials was 13. My probability is 41. And the x value is fewer than 3. So 2, 1, and 0. It will enter it for me. and I got an answer. Now, what if I added them all up using PDF? First with 0. I would get the same thing. And we can check and see what they did as well. Well, okay, they had a probability of 47%. And I put 41. 0.0192. And so it matches what we got there as well. All right, so that's going to wrap up our review. It was a little tough. There was a lot going on there. .25 would be continuous. Any decimal number, whether it goes on or not, it would be continuous in terms of the context that we're saying. You know, it's very ambiguous, and there's a lot of double meaning and different definitions. But statistics does things its own different way. But to answer your question, continuous numbers will definitely be fractions and decimals, and discrete numbers will be whole numbers, and you can describe all of the numbers in those two different ways. All right, I appreciate everybody hanging in there, and stay tuned for more updates that may happen. We're going to end the stream at this point, and I hope this was useful. It was pretty long and drawn out, and maybe next week I can create some more customized videos that may pop up. Thanks for tuning in, and Travis, good luck to you. Thank you for hanging in there, man. I really appreciate it. You came right on time.